All right, so up until now, our focus has been on dealing with homogeneous linear nth order DEs, and we've developed some useful results, how to come up with a general solution if you have a fundamental set of solutions to work with. Now we want to turn our attention to the non-homogeneous case. Still talking about nth order linear DEs, but non-homogeneous, which means this g of x right here does not equal 0. It equals some other function of x. Okay? Now, it turns out that if you're trying to solve a DE that's non-homogeneous of this type, we actually start by looking at the associated homogeneous linear equation. And most of the work actually will go into solving just that, depending on what this looks like. Once we have found that fundamental set of solutions for the associated homogeneous linear I can't even say that mouthful anymore. Once we find that fundamental set of solutions for the homogeneous case, what's left is just to find a particular solution, one specific solution to the non-homogeneous equation. We call that YP, but it's more specifically called a particular solution. So again, we're going to look for the fundamental set of solutions for the associated homogeneous case, and then one particular solution for the non-homogeneous case, and we're going to be able to put those together to get a general solution for this. Okay? So once again, it's going to be helpful for us to use this operator notation. L, I'm going to define to be the differential operator that would give me this left side up here. That means I can write my non-homogeneous equation up here much more compactly as L of y equals g of x. The associated homogeneous equation would be L of y equals 0. Okay? Now, if the y1 through yn shown here is a fundamental set of solutions, remember that means that the set of solutions here would be linearly independent, then we have seen in the previous video that the general solution for the associated homogeneous linear equation, this one right here, is this, c1y1 plus c2y2 plus all those others for all possible choices of those parameters c. So we take all of those linear combinations and we call that family of solutions yc. We call this thing the complementary function. It's complementary to the non-homogeneous equation, but we get it from the homogeneous equation, the associated homogeneous equation. Okay? So we're gonna show that if you take the complementary solution here, the complementary function, and add to it any particular solution to this non-homogeneous DE up here, then the result is a solution to this DE. In fact, it's not only a solution, it gives us the general solution. So to show why that's the case, we define y to be yc plus yp, complementary function plus particular solution. Using the fact that differential operators are linear, I can split this into L of my complementary solution plus L of my particular solution. But the complementary solution, remember, is from the associated homogeneous equation, which means this is equal to 0. This is a particular solution to the non-homogeneous equation, which would give me a g of x here. 0 plus g of x is g of x. So that y is another solution to our non-homogeneous equation that we started with. And I want to show that not only is it, just some other solution, it actually gives me the general solution. So to do that, here we've got my theorem here. This is my, again, nth order linear non-homogeneous DE that we want to find a general solution to. If you have the complementary function that goes with it and have found one particular solution to it, then y equals the complementary plus the particular is the general solution to this whole thing. Now, how do we show that? Well, what I do is I say, let's suppose we have some arbitrary solution to this DE up here. I want to show that that arbitrary solution takes on this form somehow. So I'm doing that here. Let's let this capital Y of x be any solution to that DE up there. And from that, I'm going to define a new function. U of x is going to be defined to be that capital Y of x minus the particular solution that we're supposing we have access to. Now what I'm going to do is take that linear operator, the same one we defined before, and apply it to U. So what is L of u? Well, u is defined to be capital Y minus my particular solution. Using the linearity of L, I can split that this way. Now, what is this first term? Well, L of capital Y of x. We assumed that capital Y of x was a solution to the non-homogeneous equation, which means this is equal to g of x, shown here. Our particular solution is another solution to that non-homogeneous case. So that is also g of x. That means I have g of x minus g of x, which equals 0. But that tells me that u of x is a solution to the associated homogeneous equation. And we know what the general solution for that looks like. The general solution looks like linear combinations of our fundamental set of solutions. So that means u of x is actually representable as a linear combination of the y1 through yn. Okay? Now, let's come back here. We said that u of x was defined to be capital Y of x minus yp of x. So if I take this, substitute it for that u right there, and then add the yp over my particular solution, I get that my arbitrary solution, capital Y of x, is equal to this linear combination from my fundamental set of solutions for the homogeneous plus the particular. Or in other words, this function belongs to this infinite family of solutions. And that shows that all solutions to this dE up here have to take on this form. So let's take use an example to sort of make this a little more concrete. Okay, I want to verify that this function right here, notice it's a 2-parameter family of solutions, is the general solution to this dE shown here. Notice that it's a linear second order dE, but it's non-homogeneous because it's set equal to a function of x that's not 0. So what do? One thing I could do, I could have verified this all the way back, or sorry, I could have verified that this is a solution all the way back in chapter 1 when we talked about solutions to dEs, but back then I didn't know how to determine whether this encapsulates all possible solutions or if there would exist other solutions outside of this family. And the theorem that we just talked about says that it gave us conditions to determine whether something is a general solution to this type of dE. So here, where the parameters are, this would represent YC, my complementary solution. And this here, 1/15 x squared minus 1/6 x, would correspond to YP. Okay? Now my complementary solution is a linear combination of the two functions that are going to make up my fundamental set of solutions to the associated homogeneous equation. I'm going to define y1 to equal this guy, x to the negative first power. Or sorry, negative 1/2 power. And y2 is going to be x to the negative first power. Okay? I'm going to check this one solution right here in the associated homogeneous linear equation. So I need a first and second derivative in order to do that. And that means y1 prime is going to equal negative 1/2 y to the, or sorry, x to the negative 3/2. y1 double prime is going to equal, it's going to equal positive 3/4 x to the negative 5/2. Okay? Now what I want to do is take these, plug them into the left-hand side of this equation, and I'm hoping that comes out to 0, because that would imply that this is a solution to the, excuse me, to the the associated homogeneous equation. So to do that, let's try plugging in 2x squared y double prime, which in this case is that guy, 3/4 x to the negative 5/2, plus 5x y prime plus 5x y prime, y1 prime is this guy, negative 1/2 x to the negative 3/2 plus y. Okay? Or sorry, y, I need to plug in x to the 1/2, negative 1/2 power for y. Okay? If we simplify this down, here I'm going to get 3/2 x to the negative 1/2 from this term. From this term, I'm going to get minus 5/2 x to the negative 1/2. And from here, I have plus x to the negative 1/2, which equals 0. That shows that this function is a solution to the associated homogeneous equation for this guy up here. I'm not gonna do it. I'm just gonna do like a little dot 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 here. But we would check y2 the same way, and you can verify pretty easily that it also is a solution to the associated homogeneous equation. So we have potentially a fundamental set of solutions, but I don't know if it's linearly dependent or linearly independent. I have to verify that. So that means I now want to look at my Wronskian here. So my Wronskian is going to look like x to the negative 1/2, x to the negative 1 power, and then derivatives. I want negative 1/2 x to the negative 3/2 power, and then this is going to be negative x to the negative 2nd power. Okay, now notice that these functions here are not defined at 0, right? The x to the negative 1/2, x to the negative 1, neither of those are defined at 0. So my interval of validity that I'd be working in here cannot be all real numbers. However, my interval I could be the interval from 0 to infinity. That's a possible interval of validity that I could use here. And the point of mentioning that is that my Wronskian, notice I didn't say W of the arguments here. Sometimes we just say W just for short. I could either evaluate this directly as functions, or I can pick a number from this interval, plug it in, and then check that, and still get the same result. So the number 1 is in this interval. I'm going to plug a 1 into all of this. This would equal 1, 1. If I plug a 1 in here, I'm going to get a negative 1/2. If I plug a 1 in here, I'm going to get a negative 1. What is that determinant? So 1 times negative 1 is negative 1, minus negative 1/2. That's negative 1 plus 1/2, or negative 1/2, which is not equal to 0. So we have linear independence. Again, that's good. We want that. Okay, that tells me that this is a fundamental set of solutions, the y1 and the y2 that I chose up here, which means that the set of all linear combinations of that will be a general solution to our homogeneous equation associated with this non-homogeneous one, which means that we're good on yc. Now I need to see if yp is a particular solution to that that guy right there. And I can already see I'm going to need more paper for this, so I'm going to continue this on here. Okay, so if I set this equal to this off the screen, if I set this equal to yp is equal to 1/15 x squared minus 1/6 x, then the derivative of that will equal 2/15 x minus 1/6, and the second derivative is going to equal just 2/15. Okay, now what I have to do is show that when I plug these in to my dE up here, that what I have is a particular solution to the non-homogeneous case. I want this to come out to x squared minus x this time. Okay, so let's do that. I know it's off the screen, but this is what that dE would look like after plugging these in. So 2x squared times y double prime, or yp double prime, which is 2/15, okay, plus 5x times y prime, yp prime is equal to 2/15 x minus 1/6, plus y, or yp in this case, which is 1/15 x squared minus 1/6 x, okay, and we do a bunch of simplifying. So what is this equal to? Well, this would be equal to 4/15 x squared. Distribute the 5x in here, I'm going to get plus 10, hold on, let me see. Oh, no, yeah, let's simplify that a little bit. I'm going to get 10/15 is the same thing as 2/3, I'm going to call that 2/3 x minus, multiply this, I'm going to get 5/6 x there. Oh, sorry, this is an x squared term. Make sure that's an x squared. Actually, you know what? Let me keep that as 10/15 instead of simplifying it, because I have to combine a bunch of like terms, so I might as well just do that. Okay, 10/15, sorry, that's sloppy. 10/15 x squared minus 5/6 x plus 1/15 x squared minus 1/6 x. Okay, looking at my x squared terms, 4/15 plus 10/15, that's 14/15, plus 1/15, that's 15/15, which is 1 x squared. And then I have negative 5/6x and a negative 1/6x. That does come out to just x. Okay? So that shows that this is a particular solution to that non-homogeneous equation. And those two facts together show what we wanted to show. It showed that this thing right here is the general solution to the non-homogeneous DE that we're given right there. Okay? I'm getting winded. All right. I lost my last page. We have one more thing to cover. Where did it go? Where did it go? Where did it go? Oh, here it is. I got so many pages floating around. All right, last thing. We're not doing an example to illustrate this because we're going to flesh this out a little bit more in, I think, section 2.4 when we talk about undetermined coefficients, a solution technique. The superposition principle that we talked about has a generalization that we will need a little bit later. So in this case, I'm looking at not just a single non-homogeneous linear nth order DE, but I'm going to be looking at a bunch of them, k of them in particular, but I'm going to assume that all of them have the same left side. The only thing that's different between each of these is this function here on the right-hand side. So I'm going to say let's let y of p1, y sub p1, y sub p2, all the way through y sub pk be particular solutions of these DEs. I know there's only one written here, but notice that this gi right here, this I can take on values from 1 through k. So that's a total of k different functions that I can assign to the right-hand side here. Okay. So if these guys are solutions to each of these respectively, then if I were to sum all of these and call that yp, if yp is equal to the sum of each of these particular solutions, then that is going to end up being a particular solution to this non-homogeneous DE, the one that has the same left side as this.